Hi viewers, welcome back to the second video in the series of lectures on finite element theory and practice. This set of lectures are aimed at creating awareness among the users of commercial software packages. Perhaps in the first video we saw a small example. We talked about single bar element. This was how the model looked like. We had a simple two node linear bar element, which this was the physical problem that we were solving. Then we got the displacements as, I'll skip the commands stream which was used to generate the model in ANSYS APDL. So this was the displacement, and we talked about the basic principles like linear superposition. We talked about how the finite element equations will look like, and I paused that video, or I stopped that video with two questions for you. The first question was, when you apply 1000 Newton, you got a displacement of 0.005 units, whatever be the units you are working with. Now, my first question was, instead of applying a load of 1000 Newton, you take the same model, but this time I am applying a displacement boundary condition where I am pulling this particular node by the same amount, 0.05 units. Then I asked you what would be the force here? What would be the reaction force here? Any guesses? The right answer is 1000 Newton. So these two are equivalent. These two problems are equivalent. This is very interesting. It may appear as a very simple problem to you, but when you are doing this very large finite element models and you want to do a local analysis, the one thing you can do is you can take a small chunk of the model and then do a detailed analysis. But while doing the detailed analysis, you have to make sure that at the boundaries or at the edges, the displacement boundary or displacement conditions are met, or the displacement is maintained, because it is as good as telling that the load is also transferred appropriately. Make sense? So these two problems are equivalent. So doesn't matter you apply 1000 Newton or you apply a displacement boundary condition where restraining this displacement to this much, you are doing more or less the same problem. In fact, you are doing the same problem. Okay, I had another question for you. I believe the question was this. So now I'm applying uh, 1000 Newton, but the difference is that now I'm fixing all degrees of freedom here as well. Here also I'm fixing all degrees of freedom. Here also I'm fixing all degrees of freedom. But still I'm applying 1000 Newton load. What will be the result? The answer will look something like this. You can see there is no displacement felt by the bar. Why? Because you are applying an external load to a point which is completely constrained. There is no load transfer. This is very important when you do very large models. You need to and in between assume there is a load transfer happening, and at between you are given this very rigid constraint, or there is something which holds your structure very rigidly at a point. Then most of the load will be taken at that support. There won't be load flowing down the stream. It's a very important concept. So this is the answer. When you apply both when you completely restrain that point, there won't be any load flow down the stream. Some softwares can throw an error uh, because you're applying the load at a suppressed degree of freedom. Okay, so don't apply a load at a suppressed degree of freedom, so that doesn't transfer properly. Make sense? So these are the two key takeaways in the initial session of the lecture. Now let's go ahead and see what we have got in this lecture. Pressing forward, we have another problem here. Here we have a toggle frame made of two bars. So these are the two bar elements, and we have a load application here. But before that, I would like to drive home a very simple concept. Say I have a bar element like this, and I apply a force over here. Will my FE solver solve this for me? Most probably no. Why is it? Because you didn't give the exact boundary conditions, so you need to specify that this node, whenever I draw this particular bar, actually in FE you won't see this rectangle. In FE you will just see these two nodes. So until and unless you impose a boundary condition where you say that if this is the x direction, until and unless you say that, hey mate, look at here, this node cannot move in this direction, unless and until you tell that, it won't solve. Mathematically we can say, when you don't give boundary condition, it is as good as your symmetric matrix is going singular. So I told you in finite element generally we end up with equations in this form, where your interest is to solve for u. If your k is singular, k is the stiffness matrix, is singular, then you can't get still you can get solutions, but you cannot invert it, and there are a lot of difficulties you run into. You can have a quick check here. You remember the stiffness matrix for the bar element? It looks like this. If you take the determinant of this particular matrix, it will turn out to be 0. Make sense? But when you bring in boundary conditions, k won't be singular anymore. So this is one little example to tell you how efficiently you need to remove rigid body modes from your finite element model. Make sense? Now let's get back to the toggle problem. This is the command stream that can be used to generate this model. You can pause this video and go through line after line. In case if you have some doubts, you can comment on the comment section. I will reply to that. First example, let's keep this alpha value as 45 degree. Build the model, solve it. Now this is the results which you get for the uy. Y direction is this. This is your x direction. So this is how y direction displacement looks. Makes sense, isn't it? Like you expect these 2 points to remain at the same point as it is, and you expect this point to move downwards, and it is moving downwards here, as you can see over here. Now just spend a little bit attention to your out file, or the file where it writes all the background calculations, where the error messages will throw up. In APDL it comes in a black screen, the solution information in Workbench. It's called solution information Workbench. Whatever it is, just read these values, like minimum pivot absolute value is this much, what is the maximum pivot. Just keep these two values in mind. Now let's change the alpha value to a very small value, something like 0.5 degrees, and again look at the same result. What is happening here? Now the minimum pivot value is again at node 2, but this time the value drops down to 60. It was earlier a very high value, now it drops down again. Now let me again change the alpha to 0.1 degrees. Again 0.1 degrees. The deformations are shooting up. You can see over here, when we started with alpha equal to 45 degree, this displacement was not this high. We are making it more and more flat, so we can expect more and more displacements in the y direction. And see this your solution information once again, and now you see the minimum pivot has further reduced. It has reached a value like 2.4. Now as a final exercise, let's change the alpha value to 0.01 degrees. It's pretty flat. If I draw the toggle for that, if let's say this is 0 degree straight line, the toggle corresponding to that small angle will look something like this. I'm exaggerating here, so this is the point where you're applying your 1000 Newton. So the toggle will look something like this. Make sense? Let's see what was the minimum pivot value I got. Again, every time I'm getting the minimum pivot value at the node 2, corresponding to the UY degree of freedom. So this is node 2. Let me make it clear. This is the node 2 we are talking about. Let me just go back to the command stream and clarify that for you. Yes, I was right. So you can see over here the node 2 x coordinate is 50, so that's the middle node we are talking about. So again, the small pivot value is coming at that location. Then I'm plotting it. As I'm plotting it, the minimum pivot value in absolute value, as I decrease the toggle angle, the minimum pivot value also decreases. Why is it so? So that's a question I have for you at the end of this video. I will answer it in the next video. But before I answer it, I have two more videos in this series of lectures where I talk about the stiffness matrix concept for a bar element. For both a two-noded bar element, which is in aligning along a coordinate system, aligned along a coordinate system, and I will also talk about how you can get the stiffness matrix for a general bar element which is inclined. So here we can see over here, see the global coordinate system is aligned in this way, but the bar element is aligned in this direction. So when you have bar elements aligned at a different angle, how you finally compute your stiffness matrix, that will be discussed in the next lectures. So after two more videos, like the one on the simple stiffness matrix of a bar element and the next video on the inclined bar element, then we will go ahead and answer why the pivot value is decreasing as I decrease the toggle angle. So I will have an answer on the fifth video. Thank you. Thanks for watching.